In the previous video I characterized the crystal filter, which you see the schematic for here, 20 crystals in parallel. And these are the parameters I found. The power in each crystal 0.585 milliwatts. Knowing that the voltage on the crystals was 14.2 peak to peak, I know 5.0 RMS. That gives me the impedance across all the 20 crystals as 2.15 kilo ohms. And the Q, when there is no load, was 90,000. When running in the oscillator, the impedance was 3.3 kilo ohms and the Q a little bit higher, because there was some negative impedance on the input of the subsequent amplifier. In this video I'm going to study the sideband noise of the amplifier. This group of 6 parallel J310. As a first step, I'm just now looking at the sideband noise when measuring at this point the output, and I have disconnected the amplifier that normally is connected here. I have collected the correlation spectrum for 21 hours now, and this is the phase noise, and it looks like this. Here is the amplitude noise. I have saved both the amplitude noise and the phase noise in various expansions of the X and Y scales. And here comes both of them at the same time. And the yellow is on top, that is phase noise. And the phase noise is a little bit stronger than the amplitude noise over the entire frequency range. Here is some structure caused by spurs. Here is the evaluation of the spectra that I have saved. And the phase noise, the difference when adding the amplifier is too small to give any reasonable result. For the phase noise, I do get results at close separations, but at the widest the difference is too small. I get negative values here. Plotting them on paper, this is what I see. The red trace, that is the phase noise from the crystals, which is the same as the phase noise from the crystals plus the amplifier. And the amplitude noise of the crystals is the same as the phase noise. But the green trace here, it is clearly higher, and that is with the noise from the crystals plus the noise from the amplifier. So, lesson learned, the amplifier adds flicker noise on the amplitude, but not on the phase. I have attenuated the signal from the Wenzel oscillator by 60 decibels and also changed the output coupling from the 9 ohm impedance on the sources of the FETs. I forgot to draw this capacitor, which has been there all the time, and now changed to this. This also gives an impedance of 50 ohms here, but much more signal, of course. There is no risk for saturation in the transistors at 60 decibels lower level. So I wanted to maximize the signal going into the 2-channel receiver. And here is what I see, a very smooth curve, and this is the phase noise. It has been running for 13 hours, it was running overnight, and the signal to noise ratio is very good, of course. And I can click here to get the amplitude noise. And here it comes. It looks similar. And I can click once more to get amplitude noise and phase noise at the same time. And there isn't any difference. AM noise and phase noise are equally strong. And that is exactly what one should expect, because the noise I see is the white noise. It is not sideband noise anymore. So I expand this and read the levels from the screen. So I can have 0.5 dB per division, so I can read tenths of a dB fairly well from the screen. The next section, and I still have this 0.5 dB per division. And the next one. And finally, minus 132.7 at 200 Hertz separation. So I add the minus 60 decibels attenuation and plot the thermal noise of the crystals plus the amplifier noise on the same diagram. And it's clear the contribution from that is of no concern at this signal level. The sideband noise from the crystals is the dominating problem, and there is also a little flicker noise on the amplitude from the amplifier. But the crystals determine the performance up to the output of the first amplifier stage. I can evaluate the composite noise, the SSB, with another method. This is the correlation spectrum mode 1 in the setup of Linrad. When I click on the carrier and put that into the baseband filter, I see the levels are now set to plus 0.3 and minus 0.2. So the average is close to 0. And then I click 100 Hertz away here to tune 100 Hertz away from the carrier. And here I get the noise floor, and I want a somewhat smoother curve, which I get by running slower, like this. And I want to know the level. So I wait for a while, and then I click here and drag to here. And here I can see this noise level is minus 124 dBc per hertz. And here I can see that the correlation advantage is 3.1 decibels. Now at 200 Hertz, the correlation advantage is 6.3, and the noise level is minus 126.2. And at 2 kHz offset, the correlation advantage is 15.6, and the noise floor minus 127.3. 2 kHz on the low frequency side, the correlation advantage is 16.6, and the level 126.6. This is the table from the signal analyzer graph, and here is what I found from the correlation measurement, and the values differ by 0.2 decibels. This is an error because now I'm measuring the sum of the AM noise and the phase noise, and I know that they are equal. So there is an error in the software that I have been using up to now. At 2 kilohertz, I get somewhat different results here and here, but the sum is very nearly the same. So it's minus 143.1 on the average at 2 kilohertz. The presence of a 3 dB error has been obvious since I started with this 60 decibels attenuated signal. That's clear because the correlation spectrum is about 3 dB above the power spectra, and it should never go higher. So I thought perhaps the power spectra were plotted incorrectly with respect to the scale, but as it turns out, it is the correlation spectrum, so I will have to correct that. To see the noise over a wider frequency range, I have connected a pair sieves. I have also inserted low noise amplifiers between the unit under test, this unit with the filter and amplifier, and the pair sieves. And I have still 60 decibels attenuation, and this is what I see. There are some spurs, but I click at an offset of 70 Hz. There is a spur 100 Hz away, so I want to avoid that. But here is 70 Hz offset, and I can read the noise floor. I wait a little. And what I see is minus 115 dBc per hertz. That is 10 decibels higher than the expected reading at 70 Hz, but there could be reciprocal mixing from the pair sieves. I don't need the carrier anymore because I have calibrated the gain on the scale for the S-meter graph properly with that signal. So now I disconnect the Wenzel oscillator, and again I have to wait for a while. Here you can see some noise problems I ran into. It was because I was careless. When disconnecting this cable, I just left it laying, so it made some not so good contact to something, and that's just the screen on the cable to the attenuator. I have moved it to a safe position and clear the S-meter graph and wait again. And now I see minus 124.5 as compared to minus 125.1. So that's a 0.6 decibel error. I have disconnected the device under test and instead connected a dummy load, 50 ohms, on the low noise amplifier. And I know that the test object, my unit, is accurately 50 ohms, and now again I have a 50 ohm room temperature connected to the input of the pair sieves, and now the noise floor is minus 132.2. With only 7.7 dB difference when substituting the device under test with the dummy load, I have to correct 7.7 dB, that's 5.9 times. It means that the device under test is 4.9 times above the power of minus 132.2, while the low noise amplifier is minus 132. 4.9 times, that is 6.9 dB. So I have minus 132.2 plus 6.9, that's minus 125.3. That comes very close to what I wanted to see, minus 125.1. So the measurement I do here is consistent with what I found when studying the noise with the correlation spectra. So I can measure now the noise floor with the Perseus, but since the Perseus and the low noise amplifier do not care what is the input impedance, I will connect directly to the sources of the transistors to get more signal and better precision. I placed a step-up transformer to go from 9 ohms to 36 ohms, it's a factor of 2 here, and then to the Perseus through the low noise amplifiers. I had to increase the attenuation from 60 to 80 decibels in order to not saturate anything. So I changed calibration to make the graph now show minus 20 for the increased attenuation by 20 dB. And now I see minus 126.1, while I expected minus 125.3. So that's an error of 0.8 dB, and that is within the errors expected from these 20 extra decibels I have added. Here is the noise floor with the dummy load. It's much lower, of course, but the impedance is no longer precisely 50 ohms, so there could be some little error in the measurement of this level, but it's low enough to not be of any concern. This is 1 kilohertz offset, and I see minus 139.7. That is just 3 decibels above the minus 142 I was seeing with the correlation method, but probably this is not far enough above the room temperature dummy load. I will collect that. The room temp dummy load is at minus 142, and that means that the device I was testing, which was 3 decibel above, was also at minus 142, and together they gave minus 139. So I cannot measure at larger separations with this setup. I have connected the noise figure meter now, and the noise diode is off. And I can see here the noise floor 0. And then I switch it on, and it goes to 1.6 dB now, and the noise goes up by more than 3 decibels. So the noise figure is a little bit lower. This instrument is not quite stable, but maybe something like this. So the noise figure is 1.4 dB. I cannot make it much better. And it is a room temperature system. So this preamplifier is essentially noise-free already at 1 kilohertz. But with the correlation method, of course, I can see a little bit better. From 1 kilohertz to 2 kilohertz, there was 1 decibels improvement. Now I will use the network analyzer to look at the impedance at this point, the output on the common sources of the FET, and at the same time I will look at the signal leaking backwards to the input here. And here is what I see before I touched any tuning. The impedance is 9 ohms, and I cannot see in detail as much as I want in this format, so I look for a different format. So here is the impedance magnitude, 9 ohms, on the output of the amplifier and hear what comes out from the BNC connector. I will now turn the tuning capacitors a little. So I turn this one back. That was this capacitor. Tuning for a symmetric impedance curve also gave the smallest coupling to the output. Now I will tune the other capacitor. And as you can see, it gives a similar effect. So what I have to do is to tune both of them for minimum coupling to the output. Something like this. I have connected the power amplifier and I'm now looking from the input connector through the filter and the first amplifier and through the power amplifier to the limiting output. But the level is far below where clipping occurs, so I see a gain of 3.7 decibels. I'm now looking at this point, the limited output, with the signal analyzer mode of Linrod, but I have set the input from the vent cell to only plus 3 dBm, so I am something like 6 decibels below the point where the diodes start to conduct. And this way I should see the amplitude noise in full. And I'm collecting AM noise plus phase noise. And in the beginning, phase noise is much stronger because of the phase noise on my local oscillators. We will see what happens when several hours have passed. This is 7 hours and 10 minutes later. Statistics isn't really good, but in this range here it should be good enough for me to see enough. And I will save the usual way, amplitude and phase noise. But first I switch to phase noise here to get an idea about what the accuracy is. I'm following with the mouse cursor, well, you can see on the video where the imaginary part is. And from about 150 Hertz I can read the noise sideband, the level of the phase noise, and down to about 20 Hertz here. But at 200 Hertz I cannot trust what value I might find here. And then for the amplitude noise, I get reasonable information all the way from 10 Hertz up to 200 Hertz. Note the amplitude margins, about 6 decibels. I have removed the 10 dB attenuator and now the signal level into the unit is plus 13 dBm. But the level has only increased by 5 dB, which means that the diodes are limiting by about 5 dB now. And we will see how that affects the sideband noise, AM as well as phase. 7.5 hours. I will save the information from running 13 dBm input while clipping with the diodes by about 5 dB. So the data I have, the imaginary part is reasonably well below the noise, the phase noise. And for the amplitude noise, it's the same. So I will evaluate from paper at a later stage. I have added a second amplitude limiter. The level is only reduced by a couple of tenths of a dB, but the function that is doing the limiting is now considerably sharper. And I am looking whether this makes some difference in the amplitude noise. 11.5 hours. It looks fairly similar, the spectrum I have. I look at the phase noise to see where is the imaginary part, and it's down here. So I get fairly accurate phase noise readings, and then the amplitude noise is even better. So I will save again these images and do evaluation from paper. Collecting results. At 3 dBm input, the phase noise is this line, but at 13 dBm I get this line. But I also get the amplitude noise following the same line at 3 dBm input level. Now the phase noise that goes along these curves bends here, and I don't know whether this is because I didn't measure long enough or something else, but I'm not so interested in the phase noise at this moment. The phase noise at 13 dBm has the same behavior. It goes down at this is 100 Hertz from the expected extrapolation of the straight line. Maybe I will look at that later, but the interesting thing now is that increasing from 3 dBm, that is this dotted blue line, to 13 dBm, the solid blue line, it improves from here to here. Although at 200 Hertz the difference is small. Now, adding this extra clipper, which doesn't clip much, improves by 3 or 4 dB here and by 3 dB here. So I will look at making a much harder clipping, because quite some time ago I had a very hard clipping and it looked like AM noise was reduced drastically by that. I have put a dummy load at this point where I have been looking at the sideband noise up to now, and this is the normally feedback for making an oscillator. But now there is a dummy load here, and I have removed the dummy load I have had on the output here. And instead, on this point, I have put the limiter. First a 6 dB attenuator, then the limiter, and then another 6 dB attenuator to present the reasonable impedance to the signal analyzer, the dual channel receiver. And now I see something quite different. The amplitude noise is much smaller, but the phase noise is essentially unchanged. And if I look at the different screens, here is phase noise only, and this looks perfectly normal. And then I go for amplitude noise. And this doesn't look normal. The blue here means that the signal is negative. It means that the noise voltage, the amplitude component of the noise from the 50 ohm dummy load is larger than the noise coming from the signal source. And that is because the impedance of the signal source, the impedance at the output of the limiter, is probably very low. It's a square wave and the amplitude will not change if I change the load. So there isn't noise on it. And what about sideband noise on it? I don't know, but anyway, we can follow the curve down here, down to something like minus 175 or 180. And that's the limit of the system with the current setup. I will have to make several changes, but on the other hand, this is good enough. I want to bring the amplitude noise down a bit below the phase noise, because when I read about oscillators, it is generally said that the flicker noise of amplifiers contribute to the phase noise of the oscillator. Now, I don't understand that. I thought it would just make AM noise, but I don't know. It is in a feedback loop and things can behave in ways that I don't understand intuitively. So I will make some changes on the unit to make a harder clipping. But first I will look at the waveforms I have right now. Here is the waveform. That's with the full power output and the 6 dB attenuators with this schematic. And here is the waveform at the saturated output with the diodes. I have the external limiter in line, this one, but that doesn't change the waveform, it just affects the amplitude slightly. This is not what I expected. I have to look at what is the error I made and didn't check afterwards that I did it right. Well, a simple error. I had forgotten this resistor here on the power supply. It's 5.5 ohm and the current is 0.8 amps. So it is a considerable voltage drop. I added it quite some time ago to remove low frequency noise on the power supply, because that resistor operates together with this capacitor, 47,000 microfarads. As a result, I didn't have 24 volts here anymore, a little bit below 20, and that caused the amplifier, the 28 JFETs, to saturate and generate an overtone with that ugly waveform. So I have now increased the voltage on the other side of the resistor to have 24 volts here, and I have also modified the clipper. It doesn't look like this anymore. I have changed the way the clipper is arranged. No longer from the drain, I'm taking it from the source through a big capacitor, the same inductor as before in parallel with 100 ohms, and the same capacitor as before. It's about 300 pf here, and then many diodes both ways and in parallel. Now I get the same level here I get at this point plus 10 dBm when feeding 10 dBm to the input through the crystal filter. So that's where it will oscillate as it is set now. Here is the signal analyzer output after 9 hours and 45 minutes. The amplitude noise is now much lower than before. The clipper is operating properly and it attenuates the level by about 8 decibels. So it's a much harder clipping than before, and it is giving a nicely looking square wave. I will save these results to get from paper what the levels are. The phase noise looks okay up to 200 Hz. The imaginary part down here, and here's the phase noise. But on the low side, at 10 Hz here, the signal to noise ratio is not good enough, and not even at 20 Hz. But I think the phase noise hasn't been affected by any of these changes. So it's more interesting what happens on the amplitude noise, which comes here. And for the amplitude noise, signal to noise ratio is very good at low frequency, low offsets. But at 100 Hz, it is probably no longer okay. And I don't know whether there is a contribution from the termination. On the input to the 2-channel receiver, there is a hybrid. And what I'm measuring is the difference of the noise in the dummy load, and that is on the other side of the hybrid as compared to the signal source, which isn't 50 ohm anymore because it comes from the clipper. The amplitude noise now is this dotted green curve. It is well below the phase noise, which is still the same as before, according to this curve. And it still bends here at about 100 Hz. I have reduced the number of diodes. Now there's just a single pair of 1N4148. This change caused the signal level to increase by about 1 decibel. So I have increased the input signal by 1 decibel to have the same signal level at input as I have on the output, to measure at what will happen when I make an oscillator from this. Here is 6 hours with 2 diodes for the limiting, and this is 9 hours with 8 diodes. So again, here is 8 diodes, 2 diodes, 8, 2. It seems that I have lost about 1 decibels in the range 50 to 70 Hertz or so. On the other hand, very near DC, here is the 2 diode structure, and here is 6 diodes. There is a small change here, and I don't know what it means, but the differences are small. I will make this an oscillator now. It's still an amplifier. I'm amplifying the Wenzel oscillator, and the output is, as you can see, 1.5 dB margin to saturation of the sound card. And this is 1.5 minutes. I will now switch over to make it an oscillator. The level is a little lower, so I will reduced the attenuation on the output by 1 dB. About 17 hours later, this is what I see. Amplitude noise for the upper curve and the phase noise for the lower. And I click here to get phase noise only. Here it comes. And I can compare this with the result I had before when running this unit as an oscillator. That's from the previous video, nerds60. And it looks like this. So this is the old and this is the current. The present value, the old one. The time is similar. And at very close range, this is the old one and this is the new. And it is very similar. But that's the phase noise. Now I go and compare the amplitude noise. Here is the present result, and here is what I had before in nerds60. It's obvious now I have a lot of AM noise from the power amplifier. This is at 200 Hertz, and it's about minus 171. And here is minus 164. That's about 7 dB loss. And it's the same on all frequencies. And the amplitude noise is strong enough to be visible in the power spectra, not only in the correlation spectrum. So something happened to the power amplifier, something that produces AM noise, but not on the limited output, because that is now very low in AM noise, and the phase noise is unaffected. When I was experimenting with this limiter, with different circuits to get the proper phase shift, I made a mistake and shorted the source to ground. And that crashed all the 28 JFET transistors. So I had to replace all the J310 and also the source resistor, which you have here. And I increased the current a little bit to get a better margin to running into saturation, and that was the cause of this noise. So now I will study a little bit more carefully how sideband noise is related to the current through the transistors and possibly also the voltage. And it's the power amplifier I am looking at, because the phase noise is okay, and what I'm adding in the power amp is just amplitude noise, and I want to make that a small addition. The best signal-to-noise ratio for the AM noise is here at 20 Hz. So I will look for the noise level at 20 Hz with different currents and voltages. Right now I see minus 153.1 possibly, 153. But that is after 23 minutes. I will first look a little bit at how fast this converges, so I clear the average here. And this is 8 averages, 16. And I wait a little bit longer because this is obviously not yet a valid reading. This is 1 minute and 25 seconds, and the error is about 1.5 dB. It happens to be in the direction of better than true, but if I try to make a smooth line here, it comes very close to minus 153. So it seems 10 minutes is enough for each measurement. I will verify that. This is 3 minutes, and if I try to find an average on this not quite smooth curve, I arrive very close to 153. That's 3 minutes. The mouse cursor is on minus 153, and this is 10 minutes, 1000 averages, and if I make a straight line here, I can see that the deviations from a smooth curve is in the order of half the separation between the lines here, and they are half a dB. So plus minus 0.3 decibels or so is the maximum error when I just read off the scale here. And this requires 1000 averages. Now I have set a 4 times smaller transform, FFT, so it runs 4 times faster, and the curve is much smoother. So I place the cursor on minus 153 and 20 Hertz, and still the curve is moving fairly rapidly, although it is all the time fairly smooth. And I will wait now 5 minutes or so. It's already 1300 averages after 3 minutes, but as you can see, when a new group of averages come, the curve moves significantly, almost 0.1 dB. But I can wait 10 minutes here also. 5200 averages, and now it is minus 153.2, or a little bit more than that perhaps. I will wait quite a bit longer to see how much error was in this measurement. Now 37 minutes, and the result has not changed. Not significantly anyway. So I think 10-15 minutes will give a result within plus minus 0.1 dB or so. And that's enough to investigate the sensitivity to various currents and voltages on the power amplifier. This is the resistor I was using. 15 ohms, 4 watts, wire wound. There could be some contact resistance that is noisy between the wire and the leads. So I replaced that resistor by 8 resistors, 120 ohm each. And these are metal film, they should be less noisy. And indeed, I see a small difference. The mouse cursor is on the minus 153.5 line, and the mark on the screen is 20 Hertz. And now I see minus 153.5. So it's 0.2 of a dB. Not much, but clearly significant. I have waited for quite some time because I was doing something else. I have tried some different combinations of source resistor and drain voltage. So I used 120 ohm resistors, 8 of them, 10 of them, or 7. And that is the resistance. And here are the supply voltages. That's the DC voltage on the drain. And the source voltage, and from that the current through the transistor. And I have seen here the margin to saturation of the AD. That indicates what the gain is. So the margin becomes larger here when I have a larger resistance on the source, and with a smaller source resistance the gain is higher. It means the margin to saturation of the AD is lower. The noise varies quite a lot. It goes from minus 153.5 with 15 ohms on the source, and it's not very sensitive to the voltage, but it degrades a little when I increase the voltage from 20 to 24.5. But with the bigger source resistor, 17 ohms, the optimum is at a higher drain to source voltage. I will have a look at the waveforms to see if I can understand why this is like this. Here is 17 ohms and 26 volts on the supply. It doesn't look good at all, but this has a good performance. Now I connect more source resistors like this. This is now 8, no, it is 9 resistors, and here is 8. The power is 28 dBm, 0.3 or so. And it's this case. So with 12 ohms and 20.5 volts, I have 1 decibel more. That's 29.3 or so. So the power is in the right ballpark, but the waveforms don't look nice. I will have to check the tuning, because I may have touched that while doing other experiments. So I will look at the output impedance now. The source resistor is 15 ohms and the voltage 23 on the drain. The voltage doesn't make any difference, but the source resistor makes a small difference. I changed it now to from 15 to 12 ohms, and that changes the output impedance by 1 ohm. So impedance changes are insignificant when I change currents and voltages. As it turns out, it is favorable to have the output amplifier running saturated. So I have modified accordingly. The source resistor is now 24 ohms, and I have increased the drive level a little by connecting like this. This is nearly 5 hours, and the screen looks like this. Yellow track, the upper one, is phase noise, and the lower is amplitude noise. I have the previous results for this oscillator that I made in the previous video, nerds60, and it looks like this. So this is the old, and this is what I have now. So it's pretty similar, the white track. It is better at higher offsets. This is 100 Hertz, and this is the old. But on close range, this is the old, and here is the current. The difference is small. I can go for the phase noise only. It's like this. But first, amplitude noise only. Because here I can again compare with the old result. And it's very clear the current result is much better above 100 Hertz or so. And then I can go again and compare the phase noise, but I have to do some arrangements first. Here is the phase noise from the current design, what I'm measuring right now, after 4 hours and 57 minutes. And I compare that with the saved old result after 17 hours, and the current noise is better. This is the current, and at close range the old is better. But look at the imaginary part down here. That is after 17 hours. But now it is much higher, and it does contribute a little to the result. I mean, the real part contains some of the random noise that also is illustrated by the level of the imaginary part. Signal to noise ratio is about 8 decibels here, and that is not really quite good enough. But I will not wait more, because first I will try to see whether the supply voltage makes any difference. Here is the result of testing different operating voltages to the box, from 25 volts downwards to 21, and then I also tested 27. And as it turns out, the noise at 20 Hertz offset is not changed much. Only at the highest voltage I can see it is increasing by about 1 dB. And I could see also that the compression, the AD saturation, changed a little bit with time. So I decided that a suitable supply voltage would be 24. Going directly from 27 to 24 gave the AD saturation 0.91. But quite some time later, the level had increased by 0.2 dB when it is stable in temperature. And I see minus 155, as I did before in this voltage range. So I decide the box needs 24 volts external voltage. Then, with the supply 24, the voltage on the drain of the transistors, that is this point where I supply the unit in the schematic. There is an RC filter also in the box, so the drain voltage is 22.5, and on the source I have 7 volts. That means the current is 10.7 milliamps per transistor. I could probably use significantly fewer transistors at no loss of performance. The volt on the gate is 3.84. The output power is 29.2 dBm on 10 MHz, and the second harmonic is suppressed by 20 dB, and the third by 35. So, since the Pyre amplifier is a clipping stage, it produces overtones, and there is no serious filter on the output. So that has to be added when using this signal. I have changed parameters so I can see a wider frequency range. Here is 200 Hertz and the level about minus 170. 400 Hertz. There are spurs, but it is around here. That is minus 177 or so. And then at even wider separations I start to see the DC, the frequency 0, means the peak here. I have a direct conversion system, so I cannot see the phase noise around. Here is the offset frequency, 760 Hertz or something like that. But at some even larger separation, then I can again see. But here the time, I have been waiting 24 hours, and I would have to wait about 8 times longer or more to see this properly. But I think I can conclude that this level I see here, as I hold the tool, something like this, and this line is minus 185. So, conclusion, my system is not good enough to study the sideband noise above about 300 Hertz. There are many spurs. You can see in the power spectrum the red peaks, that's channel 2, 50 Hertz, 100 Hertz, 150, 200, 300, 400. And here you can see there are 2 peaks, because here is DC and 50 Hertz on both sides, 100 Hertz, 150, 250, 350 offset from the center. And here I have something from the other side also, so I get the complex peak here. And that's why I can see there are clearly 2. I can see in both channels also. And here is the amplitude noise. It has a similar behavior. 175 is here. That is crossed at about 200 Hertz. And then here is 180. And if I go to the other side of the center part, I can see there is the imaginary part and the real part have about the same magnitude. And I have blue peaks here, that is negative values on the real part of the correlation, but these looks like spurs. So I can guess that something like here, and that is minus 185, is the level for the amplitude noise also. In this green, I'm plotting the sum of the squares of the real part and the imaginary part. So the real phase noise or amplitude noise should be below what this curve gives. And at the far end it goes down to minus 185 with some spurs. And 400 Hertz. Well, you can see that the amplitude noise is a little bit below the phase noise. And the separation becomes smaller. And at 1 kilohertz it looks like AM noise and phase noise are similar. And that is probably so, but I need another setup to see that. Remember, as I found earlier in this video, the dB scale here is probably wrong by 3 decibels. An error that has been in all the videos I made up to this point using this signal analyzer window. I will check that carefully to see if I made a mistake again and change Linrad accordingly if there is really this error. And There is also a small error of 0.2 dB according to my finding previously in this video, and I will check that more carefully, and that will be the next video to come.